All right. Hi, everybody. My name is Zach Aikman. Thanks for coming out today. I'm the lead engineer at 17-Bit. 17-Bit is a small studio located here in Seattle in the Soto district. We made a game called Skulls of the Shogun, and now we're making a game called Galak Z, the Dimensional. And I'm here today to talk to you about the process that goes into building procedural dungeons in our next game. If you're not familiar with the game, Galak Z is a top-down 2D space shooter. It's an homage to 16-bit shooters, but upgraded with modern design and modern tech. If you try to compare the game to Asteroids, Halo, Far Cry, Spelunky, or the 80s anime series Robotech, you wouldn't be wrong in any of those regards. So for those who haven't seen or heard of the game before, I'm going to jump over to a quick video so you can see what the game's about.
Product not yet.
So the game is made in Unity. We're trying our hardest to make it not look like it's made in Unity. All right, so at PAX last year, we demoed the tutorial level for the game. It was called Fourth Cave. And inside of Fourth Cave, every rock was hand-placed and sized. Every region was decorated and uniquely lit. Every enemy patrol was strategically placed. And we were very happy with the end results, but it also showed us how much work was still left to do to make a game that was full of content and fun to play. The PAX public demo also highlighted the strengths of the game for us. It showed us that the delicate placement of rocks and flora and fauna was not the most fun part of the game, the most exciting part. And so our level design approach started to shift very drastically, very quickly. We had a hunch that we could randomly generate our levels, but it wasn't clear exactly how we would go about doing that. And I had some experience generating random levels on a game I'd worked on as a student, and so I volunteered to take on the task. I've done a fair amount of reading about procedural content generation, and the one technique that immediately stood out to me for generating realistic caves was Cellular Automata. You may be familiar with Cellular Automata from John Conway's seminal Game of Life. Cellular automata just refers to a simulation performed on a grid of cells that are always either on or off and governed by a certain set of rules. These rules are applied to every cell on the grid during the simulation, and each rule examines the cell's current state, whether it's on or off, and the state of its neighbors. And if there are enough living cells surrounding a dead cell, it becomes alive. And similarly, if there are not enough living cells around a live cell, then it dies. You can sort of see that in the animation on the left with the glider pattern. The game isn't really a game. It's initialized with a starting configuration, and then the user sort of takes a step back and lets the simulation unfold. On the left is a glider, which is one of the most popular patterns in the Game of Life. It's capable of locomotion just because of the way it's set up. Which means that it can move across the grid until it hits something, and it can transmit information. So as it moves, it'll move until it hits a wall, and because it carries information with it, you can use this to set up AND gates, OR gates, XOR gates, which actually makes the Game of Life Turing complete, which is a really cool property. And on the right is an example of a much more complex moving pattern called the seal. I'd never seen this until I started researching this. I thought it was cool, and I'd include it. But remember that all this is governed by a few really, really simple rules that operate on this grid. And they were engineered to produce these kinds of results where things live and die. But what happens if we change the rule set to something a little more stable? You get something like this. And I just want to take a moment to appreciate the beauty of this shape. It's got almost everything you would need in a Galak Z level. It's got islands, narrow passageways, pockets for hiding, pockets for putting lava pools, but all of this from the same underlying tech that formed those images, the gliders and the seals on the previous slide. The only variation is a slightly different rule set and a much, much denser starting grid. The algorithm stabilizes really quickly, so after about 10 or so iterations, you have this, this shape. And here we see a step-by-step generation of a cellular automata cave using a custom editor tool that we wrote. The animation on the left shows how the cave evolves from its initial chaotic seed. We basically just fill the grid with random on and off bits and then run this, and then over time it produces that shape. The animation on the right demonstrates how the spaciousness of a cave can be controlled by filling that initial grid with either more dead cells or less dead cells. So if you have more white, you're going to have more space in the end results. And here's one giant cave that was generated by that same tool set. It looks pretty good, right? So we're done. Not even close. The problem is that this is too chaotic. It's impossible to control. You can generate this, and visually it's stunning. It's fantastic. But if you need to place interesting objects or decorations or enemies or like anything at all, making sense out of this mess is almost impossible. So from this, we can learn that cellular automata are not a good solution for generating whole levels, but they may be a good solution for generating smaller chunks. So at this point, I started experimenting with different subdivision techniques to sort of whittle down the space into more manageable regions. And one of the most popular methods, I'm sure a lot of you have used this before, is binary space partitioning. So if you're given a rect that defines the level, you can keep splitting it into smaller and smaller chunks until you're left with something you can work with. And I did this until I reached a size that we thought would make a good room size for a dungeon. And then at the end, we throw out some of the cells that weren't used. So what we're left with is sort of a mishmash of different room-sized chunks. And then inside of those chunks, we could place cellular automata caves. But then you have to connect those together somehow. And so I played around with minimum spanning trees, which are a way of connecting points in space to connect them with the shortest distance between each point. And the results, which I didn't take a screenshot of, I wish I had, was a huge mess. That's probably why I didn't take a screenshot of it, because it looked awful. But imagine every one of these nodes filled with one of those cellular automata chunks. What I saw was that the connecting corridors were sometimes too long or too angled, or they intersected the caves too much in awkward ways, or the rooms were too close together or too far apart, or there were just too many problems to solve. And I love solving problems, but all I saw ahead of me were more issues to tackle that didn't have an immediate apparent solution. So I decided to take a couple steps back and just sort of reevaluate my approach to the whole thing. And during this time of reflection, my coworker Paul pointed me to a Wikipedia page on something called Z-order curves. I honestly wish I could remember how this conversation came about. I can't, but he mentioned it at the perfect time. A Z-order curve is a mathematical function that maps multidimensional data to one-dimensional data while preserving locality of the data points. And if that makes you go, huh, that's exactly what I did too. I said that doesn't make any sense. But it's best illustrated with a picture or three. This is a z-order curve. Given an x and a y coordinate in space, the z value can be calculated by interleaving the bits of those two values. And it gives you this recursively shaped z-curve. And here I've overlaid the z-curve with a grid that shows you what that z value is. And how it maps, or how the coordinates map to a z-value. This means that you can easily traverse a two-dimensional grid by incrementing just one number instead of two. It flattens 2 dimensions into one. And here's a better look at what I mean when I say interleaving bits The zeros and ones compute that z value. So it gives you a really nice, simple way to move through two-dimensional space as if you're moving along a straight line. And as a completely tangential aside, this ordering happens to be the same thing as a depth-first traversal of a quad tree. So this has a lot of applications in things besides this talk. So that's cool and all, but how does that help us with the problem of structuring the level? Well, it turns out z-order curves can't help us, but through z-order curves, I found out about a family of other curves called space-filling curves. Now, space-filling curves are curves whose range contains the entire two-dimensional unit square. That means that if you have a 2x2, a 4x4, an 8x8, etc. square, you can ensure that every point in that space will be touched by one of these curves. And Hilbert curves are a set of curves that belong to this family. And the moment I saw this diagram, everything just sort of started falling into place. They preserve locality even better than z-order curves because the coordinates never change on two axes at once. They only ever move in one direction, which means you don't get any weird diagonal cross lines, which was a problem with the z-order curves. So to work with a Hilbert curve, you need two functions, one that maps one dimensions to two, and one that maps two dimensions to one. And the code is so small and so compact that I included it up here. That's all you need to generate this kind of diagram. So if we abandon the binary space partitioning, the minimum spanning tree stuff, and instead we were to lay the rooms of a dungeon out on a grid, it becomes a perfect match for Hilbert curves. There is, however, one glaring fault with this approach, and that is that the path is always the same. So imagine that I have a dungeon that's 4 rooms wide and 4 rooms tall. We'd expect to use a Hilbert curve whose dimension is also 4. You can see it fits perfectly, gives you a nice clean path through the space, but it's totally recognizable. It's not random at all. It looks very predictable. Even if you were to rotate the curve, it would still be pretty obvious, even to a player who doesn't have a map available. You'd be able to tell pretty quickly that you were flying through the same shape every time. So the solution was to increase the dimension of the Hilbert curve to the next power of 2, make it bigger, and then pick a random offset for that grid, and then walk along the Hilbert curve and check to see if the coordinates are contained within the offset grid. With a z-order curve, you would call this position along the curve z, but because it's a Hilbert curve, we're going to call it h. So h starts at 0, and you keep walking until you intersect this grid, and then you start sampling from that point, and that gives you your path through the dungeon. That may not make much sense, but once you see the animation of it in action, it becomes pretty obvious. So by randomly offsetting this grid, we get a different path every time. Sometimes the path will go off of the grid as you're walking along the curve, and when that happens, we simply stop and then resume the path through the dungeon when it comes back onto the grid. So this works, but the generated paths are still a little on the plain side. They're fully one-dimensional. There's only one way through. It's kind of boring. But in most cases, we're left with a handful of dead cells that were rejected because they didn't lie on that path. And so what we do is for every dead cell on the grid, we add its potential connections to other living cells to a list. And then we pick random connections from that and create dead ends in the dungeons. So dead ends are actually a very critical part of Galak Z, dead end rooms are a very critical part of Galak Z's dungeons because it's where we hide the interesting stuff. It's where we put things like loot, mission objectives, things like that. If we can't generate enough dead ends for a particular dungeon, then we just throw the whole thing away and re-roll. And because this process is so quick and so fast, we can do that several times. Usually doesn't take long until you settle on what you need, but it's quick enough that it's not really a concern. I really wanted to avoid the sort of drunken walk through a grid that you tend to do when you're generating random mazes like this. There's a lot of backtracking, and it just becomes a complicated mess. And so this was a really simple, clean sort of approach that didn't require much extra work. So now that we have our dungeon layout, we roughly know what shape it's going to take. We get to return back to the thing that started this whole mess, which was Cellular Automata. By working from the top down instead of the bottom up, we now have a lot more information about the dungeon, which helps us shape these rooms that we're going to be creating. And our approach to generating that layout adds some restrictions, but that ends up being a good thing, because usually when you're faced with a problem and you don't really know how to go about solving it, adding in restrictions and imposing constraints makes it easier to solve. There's fewer axes to explore, and so you're forced to settle in on a solution much more quickly than you might have. So here are some considerations that go into generating rooms. We decided that the cellular automata would generate rooms of a fixed size, and they're pretty small, 17 by 17. Seems arbitrary. Someone pointed out that it was 17-bit and 17, and I didn't even notice that, but I guess that's why. So this gives us enough fidelity with the cellular automata to actually get interesting cave-like features, but not make the rooms too big that we can't design them as individual encounters. Additionally, because these rooms need to be placed along a path where we know what the exits are, we need to be able to fix exits for these rooms to give them north or south or east or west exits. The cellular automata does a good job at providing the initial shape, but there's some times where you just want to make some tweaks. It's not quite right. There's a stray rock over here, or this pool is too deep, and you want to fill it in. So we'd like a way to paint over this as well and to fix little bits. Empty rooms are really boring, and so we also want a way to specify where objects can be placed, treasure, interactables, obstacles, things like that. And we also knew that we would need some metadata, some extra information about the room for picking specific rooms, maybe for a certain mission, or to only use this room at the end of the dungeon, or to only use this room for this configuration. I mean, there's other things you want to include, so we needed a way to specify that sort of data about a room. And the end result is this thing that we call the room template editor. I'd like to preface this next part by saying that I usually take a lot of pride in my tools and their appearance and their ease of use. This one emerged in such a way that we didn't spend a lot of time making it look pretty, but it does the job. Here it is on the right. It's basically a layer-based pixel painting tool that uses cellular automata at its core. So that's what gives you the seed, and then you paint over it in layers, and those layers contain information about different things that are going to go into the room. So there's two parts to this tool. At the top is that layer-based pixel painting interface. It lets our designers and our artists create a low-res template of an individual room. It looks like a jumbled mess of colors, but each color represents an individual layer that controls the placement of a different classification of objects. And below that is a panel for editing the room template's name, how spacious it is, how smooth it is, other metadata tags, and some controls for previewing how it looks in the game. And all this data gets serialized to and from JSON. We chose not to use scriptable object assets or game object prefabs. So let's take a closer look at the painting panel. Room creation becomes decidedly less complex when you go layer by layer. So the first layer, the user can paint over anomalies or add their own geometry, and in some cases you can just paint over the entire room. It defeats the purpose of using cellular automata, but that option is there, and the artists actually really like that. In the next layer, we add waypoints, which are those green dots with the red lines, and those are enemy patrol paths. And the layer after that, we have a layer for bugs, for decoration objects, for interactable objects, like sticky spores and spikes and other environmental hazards, floating obstacles, fixed obstacles, destructible barricades, loot, key items like mission objectives, and then lava pools, and finally a layer for foreground elements to help add to that sense of depth. So there's a lot that goes into it. You don't have to add things in every layer, but it gives you a lot of flexibility in terms of controlling the room's appearance and what goes into it. At any point in time, you can click on a build button, and that generates an in-game preview of the room that you're editing. And this ended up being obviously an invaluable part of the process. It's one thing to see it in that pixelated version, but to see it actually in the game was pretty much imperative for a tool like this. So we haven't addressed the matter of how do we convert this pixel-like grid into something that looks like a cave, something more palatable for the eyes. There's a reason that we use a low-res abstract language for laying out that dungeon room. and you'll see why in a little bit. So we start by turning the blocks into rocks by flood filling that black and white cellular automata grid, and that helps us pick out the polygons, the individual shapes in that room. Then we expand those points into squares. So you can see the red dot, or the two red dots, are where the cellular automata points were, and then we sort of extrude those out to make them bigger so that we can make a mesh out of those 2 points. So for each group of cells, we then take those points and we triangulate meshes out of those. Triangulation is a fairly simple algorithm. I mean, it's not simple, but it's known and it's solved, so I'm not going to go into it here. And from this, we end up with mesh objects that we can then plug into a mesh filter and add a mesh renderer and a mesh collider in Unity, and that gives us our collision data and the actual look and feel of it. So that's the interior, but then for the exterior, like that's still, obviously very, very blocky. So we want to fill it with more organic rock shapes. Sorry, these are out of sync. Okay. So the polygon exteriors, these rocks, build off of the interior mesh that we just made in the last frame. We use that same vertex data to determine where the rocks get placed. And all these rocks are prefabs already. They have their mesh filters, mesh renders, colliders, all that data is already there, and we just spawn them along the edge of the other mesh. And each rock was given a random scale just to add more variety. This was a huge performance cost to us because we didn't realize that non-uniformly scaling mesh colliders was so expensive. And when you're placing hundreds of these in a scene, it definitely starts to take a toll. And we have a custom shader on the rocks, which helps sort the rocks, because these are basically all in the same depth plane. You can try to offset them a little bit, but because we're using a perspective projection and not orthographic, you still get Z-fighting even if the rocks are a little separate, just because it doesn't quite know how to figure out the mesh bounds and sort those properly. So now that the geometry has been created, how can we populate the room with interesting objects? How do we bring this room to life and give it its own appearance? This is a good time to introduce the concept of dungeon zones. Dungeon zones, here we have one room rendered with 2 different zones. So the zones are how we give the rooms their unique aesthetic. Typically a dungeon is made up of anywhere from 1 to 4 zones, depending on its length, with zones often spanning multiple rooms. And they group different parts of a dungeon together so that it gives the player a point of reference. It's really confusing when you're flying through this giant cave if you don't know where you've been or you don't recognize certain landmarks. And so zones let the player say things like, oh, I must have circled back around, I'm back in the bug zone here. And it also allows us to extract a lot of variety from a single template. So specifically, dungeon zones control how the room is lit, what you see in the background layer, what kinds of objects you see in the foreground layer, things like obstacles and interactables, what kind of enemies inhabit the rooms. Some enemies are only populated by pirates, space pirates, it's one of our factions, or by Imperials or by bugs. Also what kind of loot you can find in the zone, and then how many of these rooms you'll find in a row in a particular zone. So like the room templates, all of this data is serialized into JSON. For prefab references like obstacles and interactables, we simply store the key into an asset bundle that's loaded at runtime. So all this it's really completely separate from Unity's default serialization. So now that we've seen how the individual rooms are formed, let's take a step up and examine the exterior of the dungeon. Floating grids of cave rooms in space look kind of weird. And so we need to wrap those sharp edges with something a little more realistic. And what's more realistic than a perfectly circular exterior? To construct the ends of the planetoid dungeon, which is what we've been building, we examine each side of the grid. And the first point of this polygon that we're building starts on one corner of the grid, and then it's projected outward. stopping when it reaches a certain distance away from the center of the dungeon. And then that's the second point. And then we sweep counterclockwise around the edge and add up all these points and place rocks as we go until we reach the other corner and then connect these together. And this happens 4 times for every side of the dungeon, and that gives you your end caps. For entrances to the dungeon, we do that process until we reach the entrance projected off onto the top of the circle, and then stop, make that one piece, and then resume from where we left off. So you get 2 separate pieces. And these entrance tunnels and the edges of the dungeon are admittedly very plain and clean and too not realistic, because they just look too manufactured. So one of our things we're going to do in the polish phase is to go back and add some dithering, some jitter to that entrance and to the edge of the planet as well, so it feels more like an asteroid in space than just a circle and some straight lines. Okay, time for a little breather. By now you should have a good grasp of what's going on in this animation, which, there we go. So a lot of things should make sense now. You have the obvious, in this example, the obvious Hilbert curve layout, the lighting of the different zones, the exterior, like all of this we've covered. And it looks great. We've had these dungeons in the game for a while, and we could end here, but we want more variety. We want to do more with the system. Like it does a lot already, but we can push it a little bit further. So in retrospect, some of these design constraints might have looked a little weird, but I knew throughout this whole process that eventually we were going to want another kind of dungeon. I knew it was going to be these space hulks. So space hulks are basically derelict, broken down ships floating through space. They're broken apart. They're about as different as you can get from that rounded organic style of the planetoids. They're boxy, they're rectangular, they're filled with metal chunks. It's as far from planets as you could get. But it's all done with the same system. So here's a view of a fully constructed Space Hulk dungeon. Already we can see there's a lot going on here that wasn't happening in the planetoids. There's a different tile set, different exterior, new floating thingies, 2 exits to the dungeon instead of just 1. It's hard to make out the details of the Space Hulk, so let's take a little closer look at it. Here's a side-by-side comparison of 2 rooms in the Space Hulk with 2 different zones. I'm sure I don't need to point out the differences again between the Space Hulk and the planetoid dungeons. So let's take a look at how this process can be adapted to make something less organic and more robotic, for lack of a better term. So dungeon template is what defines the general size, the look, and the feel of a dungeon. And like everything else, it's stored as JSON data, so it's really easy to edit. The fields here on the left don't require much explanation. We can specify the dimension in rooms of a dungeon, how wide it is, how tall it is, the range of dead ends it can have, and then a list of zones that it can pick from. The layout type contains at least one familiar term, Hilbert, and this is where we specify how the various rooms are laid out within the dungeon. The layout type can only be one or the other. It's not a both thing. We've already seen how the Hilbert layout works, so in a little bit I'll tell you about the binary layout as well. And the theme, this is probably the more interesting of the two. The theme is a collection of what I call styles, each of which controls a different element of the look and feel of a dungeon's geometry. So the cell, interior, exterior, foreground determine how the individual rooms are built. The empty cell style dictates what fills into a dead cell in a dungeon, and then the exterior determines how we build out the outside. And so, because we've pulled all that style data out into a theme, it actually lets us do something for free. This was a kind of a cool side effect. We were able to make a new dungeon type called Pirate Base. And Pirate Base is sort of a combination of the Space Hulk and the planetoid. It's as if a planetoid had been infested by a space pirate group, and they set up their own base, so they sort of like carved out their niche in the rocks. And this was done simply by replacing the interior and the exterior cell style for the planetoid dungeon. Otherwise, it's exactly the same. but it provides enough of a difference in aesthetic to feel like a different kind of environment. And this was literally just changing 2 lines of text in the JSON file. So that was a cool thing that fell out of this, this refactoring as we made the system more generic and more flexible. So I told you I'd talk about the binary dungeon layout, and here it is. So the Hilbert curves were kind of complex, took a little bit of explanation. The binary dungeon layout is actually really simple. We knew that the space hulks were going to be wider than they were tall. In fact, they're only ever two rooms tall. And so I took advantage of that to come up with a layout that takes a random number and looks at the bits. And then if the bit is 0, it leaves the y offset where it is. If it's 1, it'll elevate it. And so it creates this sort of very jagged, zigzaggy pattern, which gives us the kind of look we were going for the space hulks. Here's a short animation that shows some of the different space hulk layouts using the binary layout. So you get some interesting shapes, and it doesn't look at all like the Hilbert curve stuff. Okay, there's a lot going on here. Don't be alarmed. The dungeon template we've already looked at. It's on the right there. Everything on the left is data that's instanced when we make a new dungeon. So we take that template data, and it lets us create the graph and the layout for a dungeon. The graph is simply a way of it tells us about the main path of the dungeon, how the player would progress through, and where the dead ends are. It just gives you sort of a logical representation of the dungeon space. The layout is its corollary, and the layout tells you about the physical layout of the space rather than the logical. So those two work together, and when you want to do things with the dungeon, you're usually checking both, depending on what information you're after. And every dungeon is seeded with a single seed. So that covers how we build one dungeon, but we can do better than that. We can make more dungeons, right? I mean, if we can make 1, we can make 2. If we can make 2, we can make 3. So for a while, a level in Galak Z simply was 1 dungeon, and that got kind of boring. And we'd wanted it from the start, and finally we started refactoring and just getting things in shape to have more than 1 dungeon in a single level. And so then we came up with the level template. Level template is similar in a lot of ways to the dungeon template in terms of the things that it specifies, so that what it lets you control. You can specify a list of dungeon templates to pull from when you're generating levels, or generating dungeons, sorry. A number of dungeons in the level, and a flag to say whether or not the level is playable. So this lets us make a tutorial level template that's not in the main pool of levels that the player could encounter. And like the dungeon, it also has a layout type. But instead of being a Hilbert or a binary dungeon, Hilbert or a binary layout, we have single, radial, and horizontal. And I'll show you some examples of all those. And we also have properties. And these properties, a few of these are consistent. They apply to all the different layouts. Level padding controls the amount of space between the edges of the dungeons and the level boundaries. Dungeon padding controls the space between dungeons, and the spawn distance affects how far away from the entrance of the first dungeon the player begins. And then there's some other optional ones too, depending on the layout type that you've chosen. So you can, for the horizontal level layout, you can control the vertical offset, and for the radial layout, you can control how far away these dungeons are from each other. This is the horizontal one. It simply lays out the dungeons from left to right, and there's a random offset. It looks like it's ascending here, but it's random. And then the radial one is similar. It spreads out all the dungeons away from the center of the level by some fixed radius that you've provided. And so these two together instantly gave us a ton more flexibility in terms of what we could do with missions, what we could do with enemy encounters. Like by splitting the experience up into multiple dungeons, it just gives you a lot more room to be creative and to try interesting things. Okay, and now here's everything all together on one page. The level instance contains several dungeon instances. I have only one here because it's easier to put on one page. And then it has the level template, which we've also seen. And it also has a seed. So the seed for a level is what defines everything. Everything comes from that single number. That seed determines the seeds for all the individual dungeons and how all those choices are made. Okay, that's basically the process from start to finish. And so now I wanted to share with you guys some tips, some things that I wish I had known about when I started. They're useful in general, but especially if you're going to be doing procedural content generation, I think. The first one is use consistent frames of reference. You should pick a coordinate system and stick to it. This sounds really simple, like of course you would. Why would you change? That's dumb. Well, that's exactly what I did. The editor GUI goes from top to bottom with its y coordinate, whereas the Unity, the actual engine, y goes from bottom to top. And so I'd done all this work in the editor, going from top to bottom, and my Hilbert curve layout was like that, and the dungeon grid was like that, and then I had to do a bunch of transforming of that data in the actual engine, and it was just a big mess, and it went on for way too long. So stick with one coordinate system and don't deviate from that. The next tip is to draw pictures and keep them nearby. I'm an engineer, but I'm also very visual. Like I need to see a picture of something to help remember what it looks like. So draw some pictures on Post-it notes, put them up around your desk. Whatever it takes to keep that image fresh in your mind, especially if it's going to be a multi-week or a multi-month project, because you will forget things that you did 2 or 3 months ago. Defining a clear delegation of responsibilities is also super important. Not for your teammates, not for employees, but for the code that you're writing. One of the strengths of the system is our ability to swap out pieces to generate entirely different results. And so by keeping these systems modular and having each thing responsible for only one thing, it makes it really easy to plug and play different parts. And like you saw with the pirate base, that was totally free just because everything was so separated. This is notoriously hard to do when you're writing gameplay code in general, but it's much easier, much more straightforward when you're working with a system like this, and there's no good reason not to do that. Externalize as much of your data as possible. I think it's 2014. I think everyone knows that data-driven is the way to go. But in the heat of the moment, when you're writing something, it can be easy just to put in a hard-coded value or design something around values that could be externalized. So the more that you can pull out, the easier it is to tweak. The easier it is for your artists and for your designers to tweak too. Having other people contribute to this process is super useful. Like I couldn't have done this all on my own, and so being able to pull that data out so that others can edit it will get you a lot further. One second. Working memory is a really fascinating concept that basically boils down to this. How many things can you hold in your head at once? It's like juggling. How much can you retain at any one time? And this is particularly relevant to the discipline of programming. I'm sure a lot of you have had that moment where you're, an hour into some programming task, and someone across the room yells your name, and instantly it's like that model in your mind just shatters. It falls to the floor, breaks apart, and then you have to spend the next half hour getting back to that place again because you have to reassemble all these thoughts and hold on to them in your head at once. When designing and interacting with complex systems, it's imperative that you're able to fully grasp the extent of what you're working on. And the only way I know of to do that is with enough levels of abstraction to be able to think of it as 3 or 4 objects, and then each of those has 3 or 4 objects beneath it. And so I highly recommend figuring out your own working capacity, your own working memory limit, lowering it by about 20%, and then refactoring your code until it reaches that number. Because if you're trying to think about 15 different aspects of your procedural content system, you're going to have a really hard time. And finally, when possible, give yourself a target to work towards. We had the advantage of starting with a level that we knew worked, and so we had a good benchmark to compare everything to. And we didn't stop until what we had reached that level of quality. We didn't want anything less than that. And I think that where we're at now is a much more fun experience than what we had before. So we've surpassed that. But if you're not meeting that, then why are you doing this in the first place? And that's all I have. That's it. We actually have plenty of time for questions if you guys have any. We have some microphones up at the front here. This is being recorded, so if you don't come down and use the microphones, they're not going to pick up on any of that. So, yeah.
Hi.
Hey.
What were the benefits of using a JSON serializer over the scriptable objects and all of that?
Sure. I'm not a big fan of scriptable objects, mostly because of some of the polymorphic and interface, like generic serialization. I've tried to use it for tools before and never quite worked like I expected it to. I like JSON because it's easy for anybody to read. It's easy to change it without having to write a tool that changes it for me. I can just go in and then change some values or change the name of some fields and then change that in code and it's good to go. So I don't know, it's super flexible and super easy to read and use. So
Okay.
that's why I like it.
Thanks.
Yeah.
Hey, so I think the procedural generation stuff and the different levels of system you've described here are fascinating, but I just kind of want to get a clearer picture of the kind of the workflow you guys have used with this. So you mentioned like generating the room template things with the Cellular Automata, and I assume this is all procedurally generated at build time. You're not doing this at runtime.
Right.
So how does that fit in with like your artists, like painting those room templates and then assembling the levels and so forth?
Right. So the rooms are built at build time, but the actual construction of the geometry is all done at runtime.
Okay.
So the process is we have a big pool, a big library of rooms that have been built up over time, and our artists will go in and make a new one. Usually it involves clicking randomize several times until they find a shape that they like, and then that's the seed, and they build off that. And so as they build up this library of rooms, it just increases the number of the variety that you'll see in the dungeons. In terms of dungeon templates and level templates, we only have about 5 or 6 level templates, and then we have probably about 5 or 6 dungeon templates as well. And the dungeon templates are like big planet, medium planet, mini planet. We have like a 2x2 small planet that's used for the radial style, and the same for Space Hulk. So we have like 6 or so of those, and those have just been constructed over time. We haven't really gone back and made new ones yet. There's not really a workflow for that. It's mostly rooms.
Okay,
Yeah.
thanks.
Did you do anything specific to clean up the edges between the rooms so they didn't look super harsh in the transitions?
A little bit, but not really. Let me see if I can go back to one of those slides. Oh boy. Oh boy. Yeah. So if you look at the top of those rooms, I don't spawn rocks basically on the topmost edge, and there's enough of an overlap when those two rooms can join together that it just sort of handles itself. The rocks are jagged enough that they cover up space. So, yeah.
Thanks.
Yeah, sure. No, no one else? Oh, okay, one more.
So this is really probably kind of a follow-up on the previous question, but the path is what you're generating through with a Hilbert curve and the grid offset, right?
Yeah.
And that path defines for each kind of quadrant you have what face of the square as an enter and what faces as an exit, and then you use one of your room library that you pull in. Okay,
Exactly.
So my question is, what is when you were designing this and when you introduced this notion of the hand annotated room library, what problem did that solve for you? Like, did you experiment with doing procedural placement of the loot and patrol patterns, and you found that, wow, I just can't figure out how we do this nicely? Or why that kind of, it feels like you're sort of a little bit in an uncanny valley between like, oh, we've got all this awesome procedural stuff,
Right.
but we hand annotate it.
Right. That's actually something I should have addressed, and I have a lot of thoughts on that. I think that it's really, really hard to use procedural tools to generate content that is uniquely interesting. It usually ends up being too noisy and too random, and it just doesn't feel fun. Whereas the flip side is that handcrafted stuff, you know what it's going to be. You've already seen it before. And I think that a good approach almost always is some mix between the two. If you've seen No Man's Sky, you should check out that game. It's procedural generated, but what they do is they make these sort of templates for creatures, for ships, for all sorts of stuff, and then they have variations on those. So you'll never actually see the same object twice, but it'll look kind of like the other thing that you saw earlier. And to me, that's the best of both worlds. It gives you tons and tons of content, but still lets you have some control over what the player's going to experience.
Thanks.
Okay. I think that's it. Okay. Thanks a lot, guys. Thanks.